In this work, we have shown that shear Alfven waves can attenuate or decay via scattering from random magnetic fluctuations. Shear Alfven waves are important for both astro as well as laboratory plasmas because it suffers from least decay. In solar coronal region, it can pass through the photosphere and thus can carry the heat from the solar core until the corona. When the wave decay, the energy gets dissipated within the nearby plasma and heats up the medium, thereby increasing its temperature. Interestingly, the viscous and resistive decay of shear Alfven wave does not adequately account for the high temperature of the solar corona. Our proposed alternate mechanism shows that the attenuation because of such stochastic magnetic fields is significantly higher than the attenuation due to collisions. But we consider the linear propagation of a shear Alfven wave in an ideal incompressible plasma that has an equilibrium magnetic field B, which is B0, extended in the Z direction. Wave propagates along the field direction and has field perturbation. So this is the Z, only the derivative on space appear only on Z, and the field perturbations are B and V, small case. We can expand B in terms of B0 and the stochastic part, which is the B0 tilde, and the amplitude of the stochastic part is with the ratio of the stochastic part with the B0 is epsilon, which is a very small quantity. Thus, if we substitute Alfven velocity, which is this, in this equation 1, we get equation 3, which is this, and we can safely ignore the epsilon square terms. This equation 3, this is very important for us because we are going to take a two-pronged approach. One is the analytical solution of this equation 3, and we will find the dispersion relation of the shear Alfven wave propagating in a stochastic magnetic field, and then we will solve this equation directly, equation 3, using PyClaw or the Clawpack software, which is a well-known software. And we will see how we will compare the analytical and the numerical decay rates. For the analytical solution, we expand this by, small by, in terms of a mean by, which is the average of by, and a deviation from the mean, which is the by prime. We take the ensemble average of equation 3, which is this, where G is the Green's function, and then we also define R in terms of a correlation length and R0, which is the amplitude of the perturbation. And we take the Fourier transform of equation 5, which gives us this equation, and substitute the definition of R from here in this Fourier transform equation to get the dispersion relation. So in this equation, equation 7, we need to integrate this quantity, and then it will give us the dispersion relation of a shear Alfven wave propagating in a random magnetic or stochastic magnetic field in the Z direction.